Well, guys, so let me just let the slideshow. So today, we're going to learn about. Today we're going to learn about introduction to computing mathematics, and the learning objective for today is to understand the relevance of mathematics and computing. So the unit aims to provide an overview of mathematical skills required for computer programming. Learners will develop knowledge and understanding in the areas of mathematics that are used when working with a computer programming language. So, sorry, let me just move this. Cool. So, understand the relevance of mathematics and computing. Mathematics plays a foundational role in computing, serving as both a theoretical framework and a practical toolset that underpins almost every aspect of computer science. From developing algorithms to optimizing data processing, mathematical principles are essential in ensuring accurate, efficient, and innovative computational solutions. So the theoretical foundations of computing. There's 2 points here. The first one is that the relevance of mathematics begins at the core of computing theory. Key areas such as logic set theory, and discrete mathematics provide the language and rules that govern computational systems. Boolean algebra, for instance, is vital in digital circuit design and programming decision-making structures. In programming, conditional statements such as if, else if, rely heavily on Boolean logic to determine outcomes based on given inputs. Another example is set theory, which informs the structure and manipulation of data collections, such as lists, arrays, or databases. Operations such as union, intersection, and difference are commonly applied in database querying and artificial intelligence. So that's just a bit of background knowledge of the theoretical foundations of computing. Now, the second point is about algorithm design and analysis. Mathematics is fundamental in the design, analysis, and optimization of algorithms. Techniques such as big O notational load developers to allow developers to evaluate the time and space complexity of algorithms, providing insights into their efficiency and scalability. For instance, a sorting algorithm with a time complexity of O n log n is generally more efficient than one with O n squared, especially for large datasets. Additionally, graph theory supports the design of network models, shortest path calculations such as Dijkstra's algorithm, and social network analysis. These mathematical models are essential in applications such as GPS systems, internet routing, and machine learning. Now, just before I carry on, this session is just going to be more about like theory, and it will be quite boring reading of a slide. So I do warn you before we continue. But hopefully, as we go through, we'll have more solutions to do more mathematical equations, and it'll get more exciting. Um, but yeah, for the third point is programming and software development. Now, mathematical thinking enhances a program's ability to write robust, error-free code. Arithmetic operations, logical operators, and modular arithmetic are frequently used in loop structures, random number generation, and cryptography. For example, modular arithmetic underlies hashing functions and encryption techniques such as RSA, which are critical for data security. Furthermore, matrices and vectors play a crucial role in graphics programming, game development, and machine learning. In 3D graphics, transformation matrices are used to scale, rotate, and translate objects within a scene. So the fourth point is data analysis and machine learning. With the rise of data-driven technologies, mathematics have become even more relevant in areas such as data science and artificial intelligence. Statistics and probabilities are essential for interpreting data, making predictions, and training machine learning models. Concepts like mean, standard deviation, and correlation coefficients help developers understand patterns and anomalies within datasets. If I'm going too quick, by the way, guys, just stop me and I'll go a bit slower. But yeah, in machine learning, linear algebra and calculus are used to develop models and optimize functions. For instance, gradient descent and fundamental optimization algorithm relies on derivatives to find the minimum of a loss function. Now, cryptography and cyber security. Mathematics is the backbone of modern cryptography. Techniques such as prime number factorization, modular exponentiation, and elliptic curve theory are used to encrypt and secure data in communication systems. These methods ensure data integrity, confidentiality, and authenticity in data transactions. For example, RSA encryption, which secures millions of online transactions daily, is based on the difficulty of factorizing large prime numbers and inherently mathematical problems. So here's a table to show what real-world applications of all of the principles that we have spoken about. Some examples include cryptography. The mathematical principle, like we spoke about, is modular arithmetic and prime numbers. Now, this it says predominantly in online banking encryption, such as our RSA. That's a good real world example. Game development, again, that's got principles of like geometry and trigonometry, and in the real world example, it exists in movement and collision detection in Unity, which is kind of a game development programming language, or Unreal, another one. Data science, so this includes statistics and probability. And an example of this is predicting customer behavior within e-commerce. Artificial intelligence, so we know this is quite predominant and quite popular nowadays, and this has principles of calculus and linear algebra. It is also used in image recognition and recommendation systems, so stuff like your chat GPTs, Gemini, Copilot, and so on. Network routing, so this has a principle of graph theory, and an example of this is Google Maps, pathfinding, and internet data transmission. If you want to get that down, I'll give you a couple. 10. Sorry. But yeah, conclusion of this little section is that mathematics is not only relevant but indispensable in computing. It provides the conceptual frameworks, analytic tools, and problem-solving skills necessary for innovation and efficiency in a wide range of computing domains. From software development and data science to cybersecurity and artificial intelligence, mathematical knowledge empowers computing professionals to design systems that are both functional and future-proof. So the next section is about explaining how mathematics is used in computing. So mathematics is a fundamental tool in computing, providing the structure and logic upon which software, hardware, and algorithms are developed. It is used to solve problems, perform calculations, analyze data, and build systems that can carry out complex tasks efficiently and accurately. The application of mathematics in computing ranges from simple arithmetic operations to advanced fields such as cryptography and artificial intelligence, like we spoke about before. Now, there's several branches of mathematics that are directly applied in computing. Here are some of them. So, arithmetic and number systems. Computers process information using binary base 2 numbers, which consist of zeros and ones only. Basic arithmetic, addition, subtraction, multiplication, and division is essential for programming and hardware level computation. For example, CPU operations such as data transfer, looping conditions, and memory addressing rely on these arithmetic calculations. Boolean algebra, so this is the foundation of logic gates and control flow in programming. It uses operators such as and, or, not, which are used in conditional statements and control structures in all programming languages. For instance, in Python or Java, an if statement evaluates a Boolean expression to determine the program's next action. So for example, you put a condition on if a variable equals 2, then you would do a part of the programming, and then you can add an else to that. So if it doesn't equal 2, then you would do something else. So that's kind of that kind of uses a Boolean because it checks if this condition, which what I said was a variable equals 2, is either true or false. So yeah. Algebra and functions. So algebraic expressions and functions are used to define algorithms and solve equations within programs. Functions in programming, for example, fx equals x squared, are often based on algebraic concepts and help automate repetitive tasks or perform calculations. Discrete mathematics. This area includes set theory, logic, and combinatorics, which are critical in data structure design, database systems, and algorithm development. For example, understanding how to manipulate sets helps in filtering and retrieving information from databases. Statistics and probability. So these are some of the mathematical principles that we spoke about before. These are vital in data analysis, machine learning, and AI, artificial intelligence. They help in predicting trends, classifying data, and managing uncertainty. For example, spam filters in email systems use probability model to detect unwanted messages. Linear algebra used extensively in computer graphics, simulations, and machine learning. Linear algebra involved matrices and vectors. In game development, transformation matrices are used to rotate and move characters in a 3D environment. Graph theory. This underpins networking, social media, and pathfinding algorithms. For instance, routing algorithms like Dijkstra's use graph theory to find the shortest path between two nodes in a network. Calculus. Although less common in basic programming, calculus is used in optimization problems and machine learning. Algorithms like gradient descent use derivatives to minimize error functions. Modular arithmetic. So this form of arithmetic is essential in cryptography. For example, RSA encryption, used for secure online communication, uses modular exponentiation to encrypt and decrypt data. Again, real-world examples of mathematics in computing. So arithmetic, basic operations and logic in programming, that's the use of it in computing, and these are used loop counters in C++ or Python. Boolean algebra, so this is conditional logic in code and hardware, and like we spoke about it before, this is used in if statements in JavaScript and logic gates in processes. Discrete mathematics, so these are algorithm design and data structures, and these can be used in real world example, for example, tree traversal algorithms in search engines. Statistic and probability, so this predicts analysis and decision making. And an example of this could be Netflix recommendation engine. So what they recommend for you to watch is predicted on the probability and statistics. Linear algebra. So 3D modeling and machine learning is a use in computing, and like I mentioned before, Unity game development, TensorFlow, AI applications. These are some examples of real world scenarios for this. Graph theory, so network analysis and routing algorithms, and an example of this can be Google Maps pathfinding. Calculus, machine learning optimization, training neural networks with backpropagation as an example. And finally, modular through arithmetic is used in computing is cryptography. An example of it is SSL encryption in web browsers. So the conclusion here is that mathematics is not just a supportive element in computing, it is central to its development and implementation. By using mathematical concepts, developers and engineers are able to build more efficient, secure, and intelligent systems. Whether through logic, computation, or data analysis, mathematics enhances the problem-solving ability of computing professionals and is critical to advancing the field of computer science in the future. So this section describes the types of mathematics used for computer programming. Now, computer programming relies heavily on various types of mathematics to ensure logical reasoning, problem solving, accuracy, and efficiency. The use of mathematics enabled programmers to design algorithms, structure data, control program flow, and build secure systems. While not every programmer needs advancing mathematical knowledge, a strong grasp of key mathematical concepts is essential in many areas of software development, particularly in complex fields such as game development, artificial intelligence, and data science. So the first point is arithmetic. This is the most fundamental type of mathematics used in computer programming. It involves operations such as addition, subtraction, multiplication, and division. These are used in everything from calculating values in a loop to determining screen positions in user interfaces. An example of this could be in a Python program, arithmetic is used to calculate the average of a set of numbers, and the code could look like this: Python copy edit average equals number 1 plus number 2 plus number 3, all divided by 3, which finds out the average. Number 1, number 2, and number 3 here can also be known as variables. Boolean algebra. So Boolean algebra is crucial in programming logic. It deals with binary variables and logical operations such as and, or, and not, as mentioned before. Boolean expressions can control conditional statements, loops, and functions that make decisions. For example, in JavaScript, if user is logged in and user has access, then you would do code to grant that access, like I mentioned before. Now here you could add another else statement, or else if you wanted to put another condition, and you would do something else there. So the code would differ to this. Now, algebra in programming is used to define variables, formulate expressions, and solve equations. It helps in creating formulas that automate calculations or control program flow. Sorry. For example, algebraic expressions are used in calculating compound interest or applying physics formulas in simulation software. Discrete mathematics is concerned with distinct and separate values rather than continuous values. It includes set theory, graph theory, and logic, which are fundamental in developing algorithms, designing databases, and structuring programs. For example, data structures like trees, graphs, and queues really rely on concept from discrete mathematics. The social networks, graph theory models, friendships, and interactions are examples as well. Linear algebra. Linear algebra deals with vectors, matrices, and is particularly important in computer graphics, computer vision, and machine learning. It is used in transformations, rotations, and rendering 3D models. For example, game development. Transformation matrices are applied to move objects in a 3D space using engines like Unity or Unreal Engine, which we see a lot in games nowadays, even on consoles. Statistic probability and probability sorry. Statistics is used for analyzing data, while probability is used to handle uncertain outcomes. These are widely applied in machine learning, data science, and decision-making systems. For example, a spam filter may use probability to classify an email as spam or not spam, using a naive Bayes algorithm. Calculus is less commonly used in day-to-day programming, but is important in high-level areas like artificial intelligence, simulations, and optimization problems. It involves differentiation and integration, which are essential for tasks like minimizing error in neural networks. For example, in machine learning, a gradient descent uses derivatives to optimize algorithm during model training. Number theory explores properties of integers and is central to cryptography. Sorry. It includes prime numbers, modular arithmetic, and factorization. For example, RSA encryption algorithms use large prime numbers and modular arithmetic to secure online communications. Geometry and trigonometry. These types of mathematics are used in graphic design, game development, and simulations. Trigonometry helps to calculate angles and distances, while geometry assists in defining shapes and spatial relationships. For example, in game design, trigonometric functions such as sine and cosine are used to calculate projectile motion or camera angle. Again, these are just some real-world examples and application in programming of each type that I've just spoken about now. I won't go through this again because we've kind of covered this already. I'll quickly speak about some real world examples. So arithmetic has average calculation and loop encounters. Boolean algebra, again repeating what we said before, if, while, and for statements. Algebra has finance software and scientific calculations. Discrete mathematics has tree traversal, graph search, set operations. 3D modeling in Unity and neural networks for linear algebra. Spam filters and recommendation systems for statistics and probability. Calculus has gradient descent in neural networks. Number theory has RSA algorithm and blockchain security. And finally, geometry and trigonometry is used in game design, for example, 3D game mechanics, AR, and VR systems. And you can see also the application and programming. We spoke about this before. So yeah. The conclusion here is that each type of mathematics contributes uniquely to different areas of computer programming. While basic arithmetic and Boolean logic are used universally, more specialized areas like calculus and linear algebra become essential in advanced computing applications such as artificial intelligence, 3D modeling, and cybersecurity. A solid understanding of these mathematical principles allow programmers to create efficient, innovative, and reliable software systems. So here we're going to assess the benefits of mathematics in computing. Mathematics offers numerous benefits in the field of programming, ranging from improving problem-solving abilities to support the development of efficient and secure systems. It enables programmers and computer scientists to build logical, structured, and efficient solutions that form the backbone of modern software and hardware systems. Mathematics is not only foundational for basic programming tasks, but also critical for high-level applications in artificial intelligence, data science, cryptography, and game development. It enhances problem solving and logical thinking. Mathematics trains individuals to think logically and approach problems methodically. These skills directly transfer to computing, where developers must identify bugs, optimize algorithms, and implement logical structures in code. Boolean logic, conditionals, and flow control all require clear logical thinking grounded in mathematical principles. Here are some other points of the benefits. So it supports algorithm and design efficiency. Concepts such as algebra, combinatorics, and calculus assist in designing and analyzing algorithms using time complexity. Understanding time complexity using big O notation, for instance, allows developers to compare and choose the most efficient algorithms. Efficient algorithms save computational resources and reduce processing time, which is vital in performance-critical applications like online banking or search engines. It also enables accurate data representation and processing. These computers rely on binary and hexadecimal number systems to store and manipulate data. Mathematics ensures that data is accurately represented, transmitted, and interpreted. Without sound mathematical operation, errors would occur in arithmetic processing, affecting software accuracy. So four, it facilitates secure communication. Modern cryptography is rooted in number theory, modular arithmetic, and prime factorization. These mathematical methods are used in public key cryptographic algorithms such as RSA, which enables secure digital communications. This is essential for online transactions, email encryption, and blockchain technologies. Another point, it powers innovation in artificial intelligence and machine learning. So mathematics, especially linear algebra, statistics, and calculus, plays a crucial role in AI and machine learning. Algorithms rely on mathematical models to make predictions, recognize patterns, and learn from data. For example, gradient descent, a calculus-based technique, is widely used in training neural networks, and it also advances visual computing and game development. So mathematics, particularly geometry and trigonometry, is fundamental in computer graphics, game development, and augmented reality. It allows for 3D model, it allows for 3D modeling, camera movement, and collision detection. Without these mathematical principles, realistic visuals and simulations would not be possible. Again, here are some of the benefits and their descriptions and the example in computing. So logical thinking and problem solving improves ability to complex problems and debug code. Now this is used in Boolean logic in decision-making structures. Algorithm design and efficiency helps in analyzing time and space complexity. This is used in comparing merge sort, such as O n log n to double sort, which is O n squared. So these are just time complexities, which we will touch on later on in this course. Accurate data representation. So this ensures precise calculations and conversions. Converting between decimal and binary systems is an example in computing. Cryptography and cybersecurity enables data protection using mathematical algorithms. And an example could be implementing RSA encryption for secure communication. Artificial intelligence and machine learning supports model building, pattern recognition, and optimization. An example of this could be training neural networks within gradient descent. Computer graphics and game development facilitate object modeling and movement in digital environments. 3D rendering in Unity using transformation matrices is an example. Data analysis and decision-making allows interpretation of large datasets for meaningful insights. An example could be analysis customer behavior using statistical models. Networking and routing algorithms optimize data transmission using mathematical models. Using graph theory in internet routing protocols, such as Dijkstra's algorithm, is an example in computing. So here are some of the benefits and the examples which we can note down. Conclusion of this section is that the benefits of mathematics and computing are extensive and span multiple disciplines and applications. It enhances logical thinking, enables development of efficient systems, ensures accurate processing, and empowers innovation in emerging fields. Without mathematics, the computing industry would lack the necessary tools for building robust, secure, and intelligent systems. As technology advances, the role of mathematics in computing continues to grow in importance, making it an essential area for knowledge for every computing professional. And the final section will be about evaluating the importance of understanding mathematics for computing. The understanding of mathematics is not just beneficial but essential to the field of computing. It enables developers, engineers, and computer science to design, build, and optimize software in a logical, structured, and efficient manner. Without a solid grounding in mathematics, the ability to understand core computing principles, develop efficient algorithms, and handle large-scale data analysis would be severely compromised. Severely compromised, sorry. In evaluating its importance, it is necessary to consider the breadth of area across which mathematics applies and how it supports innovation, accuracy, security, and performance. Sorry, guys. Mathematics lays the theoretical groundwork for computing. Concepts such as logic, set theory, and discrete mathematics underpin data structures, algorithms, and programming languages. Boolean algebra, for instance, is the basis of binary operations and conditional statements, which form the control logic in software development. An understanding of these principles enables developers to write clean, logical code and anticipate how systems will respond under different conditions. Moreover, mathematical reasoning enhances a programmer's problem-solving ability. For example, debugging complex code often involves tracing through logical flows and identifying where conditions have failed, a process closely related to constructing mathematical proofs. This form of structured thinking is essential not only in programming, but also in planning software architecture and design algorithms. Efficiency is a cornerstone of computing. Mathematical understanding is critical for creating optimized solutions. Algorithm must be designed to process data using minimal time and memory, particularly its large-scale systems or real-time applications. Big O notation, which comes from mathematics, allows programmers to evaluate algorithm performance. Understanding time and space complexity is vital for choosing the most effective method for sorting, searching, or processing data. For instance, a web search engine must return results in milliseconds, even when indexing billions of pages. Mathematical knowledge allows engineers to design and refine the search algorithms so they can scale this efficiently. Cybersecurity is another area where mathematics is not only important, it is foundational. Public key encryption, such as the RSA algorithm, relies on prime number factorization and modular arithmetic, both of which are deeply mathematical. Without a solid understanding of number theory, implementing or evaluating cryptographic systems would be possible. Moreover, cryptographic security depends on computational hardness assumptions grounded in mathematics. Professionals working in this domain must be able to understand and assess these assumptions to ensure systems are secure and against evolving threats. In data-driven fields such as AI and machine learning, mathematics plays a central role. Linear algebra, calculus, and statistics are used to build models, train algorithms, and evaluate outcomes. A deep understanding of these mathematical concepts allow practitioners to go beyond using pre-built tools and actually innovate by developing new algorithms or improving existing models. An example of this could be training a neural network. It involves minimizing a loss function using gradient descent, an optimization algorithm rooted in differential calculus. Without an understanding of how gradients and derivatives work, a practitioner will not be able to tune learning rates, detect overfitting, or interpret model performance accurately. In game development, computer graphics and simulations, mathematics, especially geometry, trigonometry, and matrix transformations, is vital. Rendering 3D environments, modeling light behavior, or simulating physics-based systems all depend on mathematical equations. A graphics programmer must understand how to manipulate vectors and matrices to move objects, rotate views, or simulate natural effects. For example, a game developer working in Unity or Unreal Engine needs to apply trigonometric function to simulate character movement, projectile trajectories, or camera angles. Without understanding the math behind these operations, it would generally be difficult to achieve realism or control over the simulation environment. Critical evaluation. Whilst it is clear that mathematics underpins many core functions of computing, it's also important to acknowledge that not all roles in computing require advanced mathematical knowledge. For example, front-end developers may rely more on design, usability, and frameworks rather than complex mathematics. So this is more about styling languages such as CSS, front-end languages such as React.js. These are just frameworks of JavaScript. These do not rely so much on these concepts that we have spoken about, but they rather rely on the design and the user interface. However, in these roles, a basic understanding of logical operators, data manipulation, and simple arithmetic is still necessary. The level of mathematical understanding required can vary depending on the role. Software engineers, system architects, and AI researchers need a deeper mathematical skill set than junior developers or IT support personnel. Yet the increasing complexity of technology means that even less mathematically intensive roles are beginning to demand more technical skills, particularly as computing tasks become increasingly automated and data-driven. So, software development, the concept used are arithmetic, logic, and algebra, and it's important because it's writing logical code, managing conditions, and data operations. Algorithm design, concept used are discrete mathematics and big O notation, and it's important because of creating efficient and scalable solutions. Cryptography and cybersecurity uses concepts such as number theory and modular arithmetic. And this is important because securing data through encryption and digital signatures is its goal. AI uses linear algebra, calculus, and statistics, and it's important because of training and optimizing machine learning models. Data science, it uses probability, statistics, and set theory, and it extracts insight and predictive modeling. Game development uses geometry, trigonometry, and matrices, creating realistic graphics and physics simulation. Network engineering uses graph theory and discrete maths, and its goal is to pathfinding and data transmission efficiency. And finally, database management uses set theory and logic, and its goal is to query optimization and relational data modeling. So in conclusion, understanding mathematics is critically important in computing. It enables logical thinking, algorithmic efficiency, secure data processing, and innovation in cutting-edge technologies such as AI and cryptography. While the depth of required mathematical knowledge may vary between roles, a foundational understanding remains essential across the industry. As computing continues to evolve and grow in complexity, the demand for professionals with strong mathematical skills will only increase. Therefore, integrating mathematics into computing education and practice is not merely beneficial, it is imperative. Here are some of the references used during this presentation. So yeah, a lot of books have been used, a lot of information has been gathered, a lot of information has been said today. Like I said before, apologies for the boring reading out and a lot of information to gather. But hopefully, as this course goes on, we'll be doing more functions, more problem solving, which will get a bit more interesting, hopefully. And also this will help with your assessment or assignment. If you got any questions, any queries, kindly email the following email, or you can ask me as well. The submission of the assignment has to be done and set on this email, and the assignment submission is 2 weeks of the completion of the units and its delivery. So refer to the ebooks and journals on the Moodle for this unit, and it'll be quite good if you did some further reading as well. But yeah, for today, that's about it. That's all I've got for today. If you got any questions, by all means ask me. Otherwise, thank you for your time, and I'll see you tomorrow.
Thank you, Mr.
Yeah.
Hamza, very much.
Yeah, thank you.